in the past weeks, we have been looking at a variety of physical systems, largely one-dimensional systems, but also we have looked at the central potential problem. And over the set of lectures that I have given, we have considered physical systems both in terms of abstract operator methods and using wave mechanics, where the wave function is a function of space and time. We have not yet concentrated on dynamics. We will do so in subsequent lectures. But today, I would like to use the body of knowledge that we have acquired to look at more general systems. General in the sense of, for instance, two interacting oscillators, or perhaps even a one-dimensional oscillator, but not quite a harmonic oscillator, because you could have a Hamiltonian which has powers of A dagger A sitting in it. You could think of a situation where the particle of mass m is moving on a circle. So you can generalize whatever we have learnt to a set of new physical situations, and that is what I would like to consider today. So I would like to call these applications of whatever we have learnt. Maybe I should say some applications. So the first problem that I would like to consider is the problem of two interacting oscillators. So I have a Hamiltonian, both oscillators of mass m. So the kinetic energies are p1 squared by 2m plus p2 squared by 2m. And then we have the potential term. Both oscillators have the same angular frequency. So you have x1 squared plus x2 squared. The notation is evident because corresponding to the coordinate x1, there is linear momentum p1, and corresponding to the coordinate x2, there is linear momentum p2. But then I put in an interaction of this form. It is clear that there is an interaction because x1 and x2 are coupled through some constant lambda. Now, the first thing I know about lambda is lambda cannot be imaginary. It is a constant, and it is a real constant, because if it were imaginary, it is clear that the Hamiltonian will not be Hermitian. If I take the dagger, which means take the transpose complex conjugate, and if this had an I in it, the Hamiltonian does not behave like a Hermitian operator. So lambda is a real constant. Now my aim is to make this problem appear simpler, in the sense that I would like to decouple this into two oscillators with coordinates, say zeta and eta, and corresponding momenta p and, shall we say, little p. Of course, since the commutator x1 p1 is IH cross, x2 p2 is IH cross, and x1 p2 is 0, and so on, I would expect the same kind of commutation relations to be obeyed here, in the sense that zeta p commutator must be IH cross, and eta p commutator little p must be IH cross, and so on. So the idea is to decouple this into two oscillators by going to new coordinates zeta and eta, zeta being a function of x1 and x2, and eta being another function of x1 and x2. Similarly, these two new momenta are functions of the old momenta. To many of you, this may appear to be a pretty simple problem. Indeed it is, but it is worth going through this exercise because one learns a few things, good lessons, which are worth remembering. So let me look at this term. The simplest way to move to zeta and eta is to define an object x, a column vector, which is given by x1, x2, so that its transpose is the row x1, x2. So basically, I write this whole thing, the potential term, as half m omega squared xi kij xj. Note that I have summed over repeated indices, and I and j take values 1 and 2. So since, or I could well write this whole thing as x transpose k x. Since this is a 2-component row and that is a 2-component column, that is a 2 by 2 matrix. It is easy to see what the elements of the matrix K are. When I is equal to j, I get x1 squared and x2 squared. So that is just going to give me 1 here, and then otherwise there is a lambda x1, x2. So K is simply this object. Now the idea is to make this diagonal, and you can make K into a diagonal matrix by using a similarity transformation, which means I must find out that matrix with which I do the similarity transformation. In other words, I find a matrix S such that Sk S inverse is a diagonal matrix. Of course, in order to do that, I need to find the eigenvalues and eigenvectors of K, and that is simple. It is clear that the eigenvalues of K are 1 plus lambda and 1 minus lambda, and the eigenvectors are not normalized, are 1, 1 and 1 minus 1. Now that tells me what S is, because if I write S as the matrix made up of these eigenvectors in this manner, I can easily find S inverse. S inverse is half 1, 1, 1 minus 1. So that S inverse is identity, and because we are looking only at 2 by 2 matrices, it also implies that S inverse S is identity. So this is the matrix with which I do the similarity transformation. So basically Sk S inverse is the diagonal matrix with entries 1 plus lambda and 1 minus lambda. So how do I get K? In terms of this diagonal matrix, I have to pre-multiply this by S inverse and post-multiply that by S. Do the same thing here, and therefore I have S inverse d S is K. So x transpose Kx is the same as x transpose S inverse d Sx. It is evident that this should be the new vectors, new vectors. I'll call them zeta eta, the new coordinate zeta eta. Like I wrote x1 and x2, I am now writing zeta and eta here. So what is Sx? Sx is 1, 1, 1 minus 1 acting on x1, x2, and that just gives me x1 plus x2, x1 minus x2. as I said, the eigenvectors were not normalized. So, if we take care of that, we now have, I will have to put a root 2, this quantity by root 2 is what I want, and therefore, I have this. Recall that I had a half here, so I am splitting it up as 1 by root 2 here and 1 by root 2 there, and therefore, I do this. So, I have these objects zeta and eta. Now, correspondingly, it is clear that I can define the momenta capital P and little p as linear combinations of the old momenta. So, zeta is x1 plus x2 by root 2 and eta is x1 minus x2 by root 2. Capital P is p1 plus p2 by root 2 and little p is p1 minus p2 by root 2. It is not enough, we need to check that the commutation relations are obeyed. In other words, this should be equal to the same kind of commutation relation as x1 and p1 obeyed and x2 and p2 obeyed. So, I should get an IH cross here, and similarly eta with little p must give me an IH cross. Indeed, that is true, because if you look at the commutator of zeta with capital P, it pulls out a half outside, and x1 with p1 is IH cross and x2 with p2 in the commutator is IH cross. So, that gives me a 2 IH cross by 2, that is an IH cross. Similarly, out here x1 with p1 and minus x2 with minus p2, therefore. So, basically I have gone to a new pair of coordinates and their corresponding momenta such that I have the commutation relations obeyed. So, now I can write down my Hamiltonian in terms of zeta and eta. So, what do I get? I have h is equal to p squared by 2m plus little p squared by 2m plus. Now, look at what happens here. There is a zeta and an eta, but then the diagonal elements are 1 plus lambda and 1 minus lambda. So, I have half m omega squared times 1 plus lambda zeta squared plus half m omega squared times 1 minus lambda eta squared. So, I really have two oscillators, capital P squared by 2m plus half m omega squared 1 plus lambda zeta squared, and then little p squared by 2m plus half m omega squared 1 minus lambda eta squared. So, I have decoupled this into two oscillators. Look at the frequencies. Oscillator 1 has frequency omega 1, which is omega root of 1 plus lambda, and oscillator 2 has frequency omega 2 given by omega root of 1 minus lambda. So, while the decoupling has been accomplished, originally I had two interacting oscillators which had the same frequency. Now, there are two non-interacting oscillators, but with different frequencies. So, what is the total energy? The total energy, the first oscillator will give me an n1 plus half h cross omega 1. The second one gives me an n2 plus half h cross omega 2, where n1 and n2 are integers, positive integers, taking values 0, 1, 2, 3 and so on. What is the physically allowed range for lambda? If indeed I want it to be two separate oscillators, I know that lambda has to be less than 1 and greater than minus 1. So, minus 1 less than lambda less than plus 1. This is the physically allowed range, because I am thinking of it as two independent oscillators. Do I have a degeneracy in energy? Clearly this carries a number n, which is n1 plus n2. Do I have, or if you wish, I can write it as an ordered pair. Let me just call it En, and n is n1 plus n2, or n1 comma n2, that is the ordered pair. The point is the following: if there is a degeneracy, it means that I can have another set n1 prime, n2 prime, satisfying omega 1 n1 prime plus omega 2 n2 prime is equal to omega 1 n1 plus omega 2 n2. So, let us see what that gives us. So, I work in the physically allowed range for lambda, and I have omega 1 n1 plus omega 2 n2 is equal to omega 1 n1 prime plus omega 2 n2 prime if there is a degeneracy. So, what does that mean? It tells me that omega 1 by omega 2 is n2 prime minus n2 by n1 minus n1 prime. But remember, these are integers. So, the statement is that omega 1 by omega 2, the two frequencies, the ratio must be a rational number in order that there is degeneracy. So, what does that mean for lambda? Omega 1 is omega root of 1 plus lambda, and omega 2 is omega root of 1 minus lambda, and this is some rational number r by s. So, what does that imply for lambda? S squared times 1 plus lambda is r squared times 1 minus lambda, or lambda times s squared plus r squared is equal to r squared minus s squared. So, lambda is r squared minus s squared by r squared plus s squared. So, if there is a degeneracy, and you can see that the degeneracy is not generally there, it is there only if omega 1 by omega 2 is a rational number. So, those are very, very specific ratios that we are talking about. In fact, in general, if you had the original problem and it was there was no interaction, there would have been a degeneracy, because you are looking at a two-dimensional isotropic oscillator, and you know that there is a degeneracy in that problem. This interaction actually lifts the degeneracy. In other words, there is a degeneracy only for specific values, that is when omega 1 by omega 2 is a rational number. Now, because lambda is allowed only the range minus 1 to 1, it is clear that modulus of r squared minus s squared is less than r squared plus s squared. Let us write that properly. In order for the problem to be the problem of two uncoupled oscillators. So, this is what you have. So, in this problem, the degeneracy is not a generic feature, it happens only sometimes. What are the important lessons that one learns from this? First of all, of course, minus 1 less than lambda less than 1 is the allowed range, and degeneracy implies this. Second thing, what happens if lambda is equal to 0? Go back to the original problem. If lambda is equal to 0, you have the isotropic two-dimensional oscillator. So, oscillator and degeneracy present. Now, what happens if lambda is plus 1? Let us look at the frequencies. If lambda is plus 1, there is no omega 2, and you just have an omega 1. So, what does the Hamiltonian look like? The Hamiltonian is p squared by 2m plus little p squared by 2m plus half m omega 1 squared zeta squared. What kind of spectrum does this Hamiltonian have? Now, this p squared by 2m plus half m omega 1 squared zeta squared is just an oscillator. So, that is a discrete spectrum, n plus half h cross omega 1. But then this, any p is allowed, any value of little p is allowed. And therefore, the energy has a continuous part and a discrete part, very similar to the problem of the charged particle in a homogeneous magnetic field, which we have discussed earlier. So, the same thing happens when lambda is equal to minus 1. You will have the other oscillator. You have little p squared by 2m plus half m omega 2 squared eta squared plus capital P squared by 2m. So, the spectrum really has a part which is continuous energy spectrum. Okay. Now, what happens when lambda is outside the range? Let us imagine that lambda is greater than 1. If lambda is greater than 1, so lambda equals minus 1, again spectrum has a continuous part. Same here. Now, if lambda is greater than 1, let us look at this. Or better still here. Suppose lambda is greater than 1 and x1 and x2 take large values, with x1 and x2 being of opposite signs. Then surely this potential term, this whole thing becomes negative and the potential gets unbounded. So, it is an unbounded spectrum in general, unbounded potential. And that is the reason why we do not want to discuss it. It is not as if there is a lower bound for the potential term. So, these are the very many features that come out of this problem. You see a situation which is equivalent to the two-dimensional oscillator, and therefore, there is a degeneracy. You see a situation where the degeneracy gets lifted, and you have a degeneracy only for very specific values of the ratio of the frequencies. Then you see a situation where there is a discrete part contribution to the energy and there is a continuous part. Then the other case is the one where the potential is unbounded, and therefore, you do not want to consider that. So, these are the very many aspects that you can see from this problem. This is an example of two oscillators which are interacting with each other. The next example I want to talk about, the next application, is to that of a single one-dimensional case, but where the Hamiltonian is not merely of the form A dagger A, but has higher powers of A dagger and A present in it. So, let us look at the next problem. So, I give you a Hamiltonian. This is my next problem. The Hamiltonian is A dagger A plus some constant, real constant G, and there is an A dagger squared A plus A dagger squared, it is Hermitian conjugate, plus A dagger A squared, it is Hermitian conjugate, plus G A dagger squared A squared then this is Hermitian in itself. And this guy is the Hermitian conjugate of that. Now you look at this Hamiltonian. First of all, this Hamiltonian has a lot of significance when we deal with nonlinear optical media. As you know, I have used the harmonic oscillator Hamiltonian extensively in explaining aspects of quantum optics. Normally, I would have worked with just A dagger A. Now, if I put in an A dagger squared, A squared term, that effectively models a nonlinear optical medium. Nonlinear because it has more than one power of A dagger and A, and the same thing happens here. So there are physically realizable optical media, nonlinear media, which can be modeled by this Hamiltonian. Is it possible, let me ask the same question that I asked in the earlier problem. Is it possible to define an A and an A dagger such that A dagger A equals this Hamiltonian? Now, I can do that just by inspection, because if I write A as A plus GA squared, then A dagger is A dagger plus G A dagger squared, and A dagger A is A dagger plus G A dagger squared times A plus G A squared. Keep the order the same because A and A dagger do not commute with each other. So, the first term is A dagger A, and then you have a G A dagger squared A plus G A dagger A squared plus G squared, that is the G squared A dagger squared A squared. So, indeed it is true that this is an example of a Hamiltonian which can be written in this diagonal form A dagger A, except that A and A dagger themselves have quadratic terms in little a squared and little a dagger squared respectively. What about the spectrum? While the spectrum itself is a little bit messy to get, first of all, is the ground state of the harmonic oscillator also a ground state of this Hamiltonian? That is true, because A dagger A acting on ket 0 is 0, because little a on ket 0 is 0 and A squared on ket 0 is 0. So, it really does not matter what happens here. A on ket 0 is 0. And therefore, it is true that both this Hamiltonian and the harmonic oscillator Hamiltonian have ket 0 as the lowest energy state. Having said that, in contrast to the earlier problem, this transformation from little a and little a dagger to capital A and capital A dagger does not preserve the commutation relation, because if you now find commutator of A with A dagger, well, the first term is A with A dagger, which is 1, and then there is an A with A dagger squared. So, there is a plus G commutator of A with A dagger squared, plus there is a commutator of A squared with A dagger, and of course, there is a commutator of A squared with A dagger squared. Now, none of these vanish. Use the ABC rule, and this just gives me an A dagger plus A dagger, that is a 2A dagger, and this is a 2A, and then of course, there is this object. So, this transformation does not preserve the commutation relation, in contrast to the earlier problem that I spoke about. Now, suppose we look at the harmonic oscillator itself, and that is by way of as an aside. Suppose I forget all this and I just looked at a Hamiltonian, the standard oscillator Hamiltonian A dagger A, but instead now I want to go to the position representation. So, I start with an operator minus d2 by dx squared plus x squared and you will recognize this as essentially the harmonic oscillator Hamiltonian. This is the del squared part of p squared, and there is an x squared, and clearly I have scaled out things, set m equals 1 and so on. 2m equals 1, h cross equals 1 and things like that. But then you see, if I now want to look, let me just do this problem. I want to look out for an eigenstate psi of this Hamiltonian. I started with e to the minus a x squared. I am not normalizing it, but suppose I started with this because that is a twice differential that is going to come out. So you can see that this is minus d by dx of d by dx of psi, tri psi equals this, not normalized, plus x squared e to the minus a x squared. Now that is a 2a. So the first term is just e to the minus a x squared and the second term is minus 2a x squared e to the minus a x squared. Plus x squared e to the minus a x squared. Now it is clear that once I cancel these things out, I need a number. So basically all that should survive is the first term 2a. If at all this should be an eigenvalue problem, I should get lambda e to the minus a x squared, which of course I have cancelled out. I have cancelled out e to the minus a x squared all over. So this 2a should be equal to lambda, which means that the coefficients of the x squared term should go to 0. So I basically have minus 4a squared plus 1 equals 0, or a squared is quarter, or a is plus or minus half. But if I use a equals plus half here, that is okay, because things are all right. When a is minus half, I have an e to the plus x squared that blows up, and no longer am I in a position to normalize it. So therefore I get a is equal to plus half, and my wave function would be minus x squared by 2 apart from a normalization. Now you also know that this ground state of the harmonic oscillator, not only this state but all the ground state, the first excited state, second excited state and so on, you can find out expectation value of x. You can also find out expectation x squared, and as you know expectation x is 0, you can find out expectation x squared in these states, and since it is a Gaussian, what survives is expectation x to the 2n can be written in terms of expectation x squared, n equals 1, 2, 3 and so on. Because it is a Gaussian, all these higher even moments can be written in terms of expectation x squared. Leave it to you as an exercise to do this problem and find out how exactly expectation x to the 2n is related, can be written in terms of expectation x squared. That is because it is a Gaussian. Now let us move on to the next application. So much for the harmonic oscillator problem and its cousins and ramifications. Let us do another problem, which is working out the Schrodinger equation solution, the wave function, on a circle. That again teaches us several lessons. So basically I want to now look at the next application, the Schrodinger equation on a circle. Before that, let us consider a one-dimensional Schrodinger equation with time dependence. And you know that the equation is this. In fact, when you looked for stationary state solutions, you wrote psi of xt as some phi of x, t of t, or chi of t is perhaps a notation that I used, or you do not quite recall, maybe f of t. And then when you did this, when you substituted it here, you got two equations. Let us just go through that. Delta by delta t of phi of x f of t is minus h cross squared by 2m delta 2 by delta x squared phi of x f of t. So, this just pulled out a phi of x, and I had an IH cross delta f of t. Now, it is df of t, because partial derivatives have become total derivatives here, is minus h cross squared by 2m f of t d2 phi of x by dx squared. Then of course, the standard trick, done it many times, divide by phi of x f of t, and this will give me a 1 by phi of x. And we said that since this object is only a function of t and that is only a function of x, each of this should be equal to some constant E. That gave me the equation for df of t by dt, one by IH cross E f of t and the solution of course was e to the minus IET by h cross. But that is as far as f of t is concerned. Look at the equation for phi of x. I have minus h cross squared by 2m d2 phi of x by dx squared equals E phi of x. So, take this to that side. This is equal to minus 2m E by h cross squared, and therefore, d2 phi of x by dx squared plus 2m E by h cross squared phi of x equals 0. So, essentially this is the kind of equation that we have been looking at. Now, suppose I also had a potential, of course, there would be an E minus V there. The important thing to note is the following, that if I were working with a particle in a box of size 0 to L, suppose x went from 0 to L, what kind of boundary conditions can I impose on this? See, first of all, I have to be careful. It depends upon the barriers. There is no translation invariance in this case, because clearly if there is a barrier, an infinite barrier at x is equal to L, then the boundary condition there is very different from the boundary condition at x is equal to 0 if that is a finite well on that side. Now, you look at this particle on a circle. So, this is the equation. I am going to think of a circle whose circumference is L, I want to keep track of the length dimension, therefore, I call it L. I could have chosen 1, but then I decided to call it L because I want to keep track of the length scale in the problem. And now, on this circle I have this particle of mass m which is moving around, got the temporal solution, but now look at the space part. What kind of boundary conditions should I impose? Now, this is some k squared, therefore, the general solution is simply going to be phi of x, some a sine kx plus b cos kx. I could start off by saying that on this circle, if I start at some point which I call 0, then when I come back, that means I have travelled a length L, phi at 0, phi of 0 must be equal to phi of L. But I also realize that there is nothing special about this point. I could have started from any point on the circle, and if I go round it once, I would expect periodicity, that is, I would expect that the wave function comes back to itself. Now, this is not new to you. You did this when, in a sense, when you did separation of variables in the problem of finding eigenvalues for the orbital angular momentum. And then you wrote the wave function as a function of r, theta and phi, spherical polar coordinates. And then the equation for the phi dependent part crucially fixed the values for the magnetic quantum number to be integers, not half integers, because you demanded single valuedness of the wave function. So, it is precisely that kind of thing that I would do here, except that I could have started with any x, of course, and I should come back to the same point and nothing should change. So, I have phi of x equals phi of x plus L. That is fine as it goes, but what about the derivative? Should I also impose a condition? After all, this is a second order equation. Should I also impose a condition phi prime of x equals phi prime of x plus L, x being any point on the circle? Suppose I did that. Remember, I have two unknowns here, a and b. So, phi of the first condition implies that a sine kx plus b cos kx equals a sine kx plus L plus b cos kx plus L. That is the first condition. Now, look at the second condition, ka cos kx minus kb sin kx equals ka cos kx plus L minus kb sin kx plus L. That is the second condition, call that 4. But you see, if I want to solve for a and b, and if I want to do that, the determinant should be 0. Now, if you solve this equation and find out what the determinant implies, it simply tells you that cos kl is 1. You can solve for that. You want to solve for a and b, and you have these two conditions, and that tells me that cos kl is equal to 1, which implies that k is 2n pi by L. N can take values 0, 1, 2, 3 and so on. But now, if I substitute that back there, I will find that I can at best get a by b. I will not be in a position to determine a and b separately. So, what exactly is the problem? It is evident that the problem has arisen because I have put in these two conditions and I am not able to consistently solve. I do not seem to have enough information to solve for a and b. The manner in which we resolve this problem is to say the following. First of all, we know that there is translation invariance on the circle. It is a free particle, in contrast to the square potential and so on, where the particle was subject to a potential v of x, a non-zero v of x. In this case, your Hamiltonian is simply p squared by 2m, where p is the linear momentum of the particle. So, it is clear that because there is translation invariance, momentum is a good quantum number. I have already discussed in a different context what you mean by a good quantum number. The context of the of conservation laws in general, I told you that the total angular momentum is a good quantum number, not necessarily the orbital angular momentum or the spin angular or the spin, because J, which is L plus S vector addition, is what is conserved in any process, be it a strong, weak, electromagnetic, any process. Therefore, I said that J was a good quantum number, and that had ramifications because J squared commutes with the Hamiltonian, and the outcome of the whole thing was the usage, the importance of the spin orbit coupling, for instance, in discussing the shell model of the nucleus. So, similarly here P is a good quantum number, P commutes with the Hamiltonian. So, it should be possible to find eigenstates of P and the Hamiltonian. I have in the position representation, I have IH cross minus IH cross d by dx, phi of x is equal to some E phi of x. Can well find the solution to this phi of x. But then you see, if I wrote P phi of x is some P phi of x, let me just call it P so that I avoid confusion. Then I just have the solution phi of x as e to the I p x by h cross. You see, this P is a number, it is the eigenvalue here of the momentum operator, because phi of x is a simultaneous eigenstate of both the momentum operator and the Hamiltonian. Call this capital P, the same P that appears there. And now if I say phi of x plus L is equal to phi of x, that tells me that e to the I p L by h cross is 1, or this momentum eigenvalue is quantized. This becomes 2n pi h cross by L, n being an integer 0, 1, 2, 3. So, you see the whole business of demanding single valuedness of the wave function on the circle tells me that the momentum is quantized and it is of the form 2n pi h cross by L. Needless to say that now we can find the energy. So, the energy itself for this particle moving on a circle is obviously quantized, and E sub n, which is the energy, is p squared by 2m, and since p is quantized, you just have 4n squared pi squared h cross squared by 2ml squared, or let us just put a 2 here. That gives me a 2n squared pi squared h cross squared by ml squared, n taking integer values, non-negative values. So, this is the energy quantization. As to the solution itself, the solution happens to be of the form e to the I p x by h cross. This is a plane wave kind of solution, and that is because on the circle there is no block anywhere. We are considering a particle moving freely on the circle. So, it is not as if it can hit a barrier somewhere on the circle and bounce back. So, the question of forming a standing wave does not arise. So, the only solutions that are allowed are plane wave solutions, and momentum itself is quantized on the circle. Therefore, the energy also is quantized on the circle. So, this is the difference that you see when you look at the Schrodinger equation on a circle compared to working with the Schrodinger equation in a one-dimensional along the x-axis without using periodic boundary conditions. So, the only boundary condition I use is this, the single valuedness, phi of x is phi of x plus L, and that should give me momentum quantization and energy quantization. So, we will look at the next application which has a lot of significance, because now that we have started doing dynamics and we are invoking the time dependent Schrodinger equation, you ask the following question. Till now we have only looked at a situation where IH cross d psi of t by dt is h psi, and I have used a Hamiltonian which is conservative. So, h is not a function of time. Then the formal solution for psi of t is e to the minus iht by h cross psi of 0. Or if my initial time were some t naught, psi of t in terms of t naught would be e to the minus iht minus t naught by h cross psi of t naught. It is convenient to set t naught equals 0, and that is what I have done here. So, it is the state vector that evolves in time, and the time evolution, the dynamics of the state vector is given in terms of the Schrodinger equation. This is a unitary operator by its very structure, because the Hamiltonian is Hermitian and you have e to the minus I times the Hermitian operator. Now, even if h were a function of time, we will consider that a little later, still the evolution is a unitary evolution, and psi of t would be related by some unitary operator to psi of 0. It is a unitary operator acting on psi of 0, though it does not have such a simple form. So, given psi of t, what about the operators? Consider an operator A. The operator itself, of course, it is a linear operator. The operator itself does not evolve in time in the following sense. There is no evolution equation which tells you how exactly this operator evolves. On the other hand, nothing prevents this operator from having an explicit time dependence. If this is the harmonic oscillator lowering operator, you can have a cos omega t, you could have a sin omega t, anything. You can have an explicit time dependence. So, any time evolution of this operator would only be because of explicit time dependence, and in the absence of such time dependence, there is really nothing to say about the evolution of this operator. Now, this I call the Schrodinger picture. So, in the Schrodinger picture, state vectors evolve in time guided by the Schrodinger equation. Any time evolution of operators is only through possible explicit time dependence. So, it is not as if there should not be a time dependence in an operator. It has to be an explicit time dependence, that is all. So, if you look at an expectation value like psi of t a psi of t, this is the same as psi of 0 u inverse a u psi of 0. Remember that psi of t is u psi of 0. I call this operator u. U would normally be a function of t comma t naught. I have set t naught to be 0. So, this would be u of t comma t naught, this u inverse of t comma t naught. So, this is what you have. Now, if A itself in the process went to UA U inverse, then clearly expectation values do not change, because psi of t A psi of t would simply be equal to U inverse U cancels, and you have psi of 0 A psi of 0, and the expectation value does not change in time. This is what we know in the Schrodinger picture. On the other hand, I can think of a formalism which is more close to matters in classical physics, where dynamical variables evolve in time. And that is called the Heisenberg picture, where the operators have a time dependence and the state vectors do not have time dependence. So the evolution equation will be an equation for operators. That is called the Heisenberg picture, and I will take that up in the next lecture.